In this video, we're going to have a quick look at the advanced information and some of the core knowledge you need to know. This won't be looking at any exam technique, it will just focus on key knowledge. Okay, so the first thing you need to know about is the CPU. You need to know the purpose CPU. The CPU is a processing device inside your computer. It is responsible for running the instructions of your programs. It stands for Central Processing Unit. It also controls the other parts of your computer. It is broken down into three main parts. We have the ALU, the CU, and we have the registers. One of the most important things to remember is the CPU is a separate device to RAM and your storage devices. In order for a program to run, it first needs to be loaded up into RAM. It will be loaded from secondary storage, which is our permanent storage, into RAM, and then be fetched one instruction and data item at a time into the CPU. The CPU is responsible for controlling that process and for all the fetching. Now, when we are talking about computers, we tend to be talking about the von Neumann architecture. So when you see the term von Neumann architecture in the exam, what this is really referring to is a normal computer. The von Neumann architecture is a stored program computer. What that means is the programs that you run are stored inside secondary storage. Then it is fetched into the CPU like I've just described, okay, using something known as the FDE cycle, or fetch, decode, execute cycle, which I'll mention in a bit. Now, in order for this to work, we also have a number of components that you need to know about. The CPU registers. Now, these are small blocks of volatile memory which sit inside the CPU. They're incredibly fast. Okay, they run at the same speed as the CPU, but they're very limited in size. There are two types. You have special purpose registers, and you also have generic registers. Both of them are used to aid the execution of your instructions. We have the CU. The CU stands for Control Unit. It is responsible for managing, decoding, executing your instructions. It also will control the other parts of your computer and manage the synchronization of your instructions to make sure that everything runs in sync with each other. The ALU is probably the easiest component to understand. It's the arithmetic logic unit. It is responsible for doing your maths, your arithmetics, and your logic such as greater than, less than, and things like that. It makes use of a special register called the ACC, or accumulator, and that accumulator is responsible for storing the results of your calculations and is used during calculations as well. So remember, your von Neumann architecture is a stored program architecture. So in order for this to work, we have to fetch the instructions from storage into RAM and then from RAM into CPU. Instructions are fetched one at a time using the fetch, decode, and execute cycle. This is sometimes also known as fetch, decode, execute, and reset or repeat. So the fetch will send the instruction from RAM into the CPU. Okay, we're only allowed to do one instruction at a time or one bit of data at a time. Once it is inside the CPU, we'll decode it. What that means is it will look at whatever the binary is and work out what instruction is that. Is it an add? Is it subtract? Is it multiply? What is it? And then finally, once it knows what it is, it can execute it. And this means simply running the instruction, and then once it's run, it can then move on to the next stage. Each one of these little cycles will take one clock cycle. Okay, so that's essentially one full loop of the FD cycle. So if you have a CPU which has a clock cycle or clock speed of 1 Hertz, that means it can do an FD cycle once per second. If it has a 100 Hertz processor, it can do 100 times a second. If it's a 1 gigahertz, remember giga is a billion, that'll be 1 billion instructions per second. Special purpose registers that you need to be aware of, the program counter, which stores the address of the next instruction to be fetched. We have the MAR, or memory address register. And now this one is storing the address of the instruction I'm about to fetch. So it's going to point to a location in memory where the instruction is located, and then the instruction, once fetched, will be placed inside the MDR, or the memory data register. So the MAR is responsible for saying where in RAM can I find the instruction, and the MDR is responsible for storing it once it has been fetched. Once it's ready to be executed, it's placed inside the CIR, or the current instruction register, and that's where it will be executed, and any registers that need to be updated will be updated. The FD cycle, it's not necessary that you know this, okay? You just need to know the fetch, decode, execute. You don't need to know how all the registers play together. However, if you want to look over that one, you're most welcome to. Let's look at RAM, ROM and virtual memory next. When we load things from secondary storage into RAM, we're doing so to improve the speed of execution of instructions. Remember that storage devices are fairly slow devices. So the order of speed, the CPU is the fastest device, then we have RAM, and then finally we have storage. Obviously, if we were talking about cache memory as well, we'd be placing that in between in terms of order of speed, the CPU and RAM. Okay. However, CPU performance is not on the advanced information, but obviously you should have a little look over it just in case it pops up inside the question. So RAM can be written to and read from. Okay, it's temporary storage. Okay, it's volatile. That means that when the power is switched off, all the data inside RAM is lost. This is the downside of RAM, but the purpose of it, the reason why we have it, is because it is fast. Okay, so we load our files from storage into RAM, and then using the FD cycle, we can fetch instructions and data one at a time into the CPU, and that process actually speeds the system up. So when we open a document, when we open a program, when we are working on any kind of variables inside our own coding, all of those we place inside RAM, and they're there temporarily until we press save on our documents, or we save something into a file if we're doing programming and things like that. So data is held in RAM will be lost if the power is turned off. Because ROM is not talked about as often as RAM, it is very common for people to make mistakes on ROM, so please do make sure you do revise over this. ROM stands for read-only memory. It is where we will store the instructions to help the computer boot up. It does not store the operating system, it boots the operating system up. What that means is it's responsible for knowing where the operating system can be found inside secondary storage and telling it to start up, basically to tell the CPU to start running the instructions of the iOS. We do not store the operating system inside ROM because the operating system is constantly updated with bug fixes and new features, and because ROM is read-only, we cannot change ROM. We can't make those updates inside ROM, therefore we do not store the operating system in there. So it boots the operating system, it doesn't store it. It performs the power on self-test. This is a very simple set of tests to make sure everything's working, like is the keyboard plugged in and things like that, is RAM connected, and so on and so forth. So we do say it stores system software because this boot up software is still system software. It stores the BIOS, okay, so the basic input-output system, and obviously its modern counterpart, the UFEI, which is essentially the same thing, just more advanced. ROM is non-volatile, which means the power, when it's switched off, is not lost. It's permanent storage. Do not confuse ROM and storage devices. Okay, storage is where we can update it, we can save our files into it. ROM, we cannot save files into it. It is fixed, it's read-only. Virtual memory is a kind of an extension to RAM. Okay, so when RAM is full, so this means that we've loaded up loads of programs, opened up loads of files, we might have run out of RAM, and then what happens is we use a secondary storage device as an additional section of RAM effectively. So it becomes an extension of RAM by using secondary storage. So what happens is some part of the program that is not currently being used, and that's really important, it's not currently being used, will be swapped and copied into secondary storage. Okay, so we swap out part of what's in RAM to secondary storage. Then that creates a space inside our normal RAM, and then we will load up a program or file or data into that space. Anything that is in virtual memory, i.e. that's stored on secondary storage, must be loaded back into RAM in order to be used. Okay, so if something gets swapped out into a secondary storage, into virtual memory, then if I want to use it later, I have to swap it back in again. So that becomes a problem with virtual memory. Although it allows us to load more things up, because we use secondary storage, there is a massive slowdown. So if any thing needs to be used from virtual memory, we have to load back in, which takes a lot longer. So if we have a situation where we're using secondary storage a lot, so a file is being swapped out of RAM into secondary storage and then back in again, then back out, then back in, this is a significant slowdown on the PC, and it creates a problem known as thrashing. So thrashing is where data instructions are constantly being swapped in and out of virtual memory because there's not enough space inside RAM, and we're having to make extensive use of virtual memory. So storage devices, one of the key mistakes people make is when they hear the phrase secondary storage. Secondary storage just means it's the second place data tends to go. So primary will be RAM, so that's where it ends up first because I edit the document, for example. And then it gets saved to secondary storage because it's the second place we put things, for example, like the hard drive, things like that. It is not external drives, okay? This is still internal inside the computer. So secondary storage stores files and programs permanently. So that's a big difference between RAM, which is temporary, secondary storage, which is permanent. It is non-volatile, and it's a lot slower than RAM. Even solid state is slower than RAM, and that's really important to remember. And there are 3 types you need to be aware of. With the 3 types, you need to know why we might use one over the other. That means you need to know its capabilities. So let's look at those. So magnetic drives have moving parts, okay, so the disk spins inside it, and you use magnetic flux to actually save the data in it. Tends to be used inside desktop computers and servers, okay. It has the largest capacity, that means that it can store the most data on it. It is fast enough for most everyday uses, okay, so it's not the fastest drive, it's not the slowest, so it's fast enough for your average kind of like loading up a Word document. However, if your performance is an issue, it wouldn't be fast enough. It's not portable, so that spinning disk when it's moving is easily damaged, therefore it's not portable. It is cheaper per gigabyte than solid state, okay. It is reliable, so if it's just staying one place, it can be relied on for a long period of time. However, obviously if we start moving it, then that becomes an issue. And it is not durable for the because of those moving parts, especially if we are moving it around. Optical drives, and this is where we'll have a disc such as a DVD disc or a Blu-ray or CD, and lasers are used to read and write data from it. We tend to use this for software installation and distribution. So for example, if I was going to buy an Xbox game, I'd probably buy it on a disc, assuming you're not doing it online. So they have the smallest capacity in reality, the slow access time, and they are portable, so it's easy to move them around. They are the cheapest out of the 3 devices, but they are not durable due to the fact they can be damaged easily. The final one, solid state, this tends to be the answer to most things, if I'm honest. It's also known as flash memory. That does throw people a little bit, so flash memory is another way of explaining solid state. It tends to be used inside mobile phones, digital cameras, essentially any portable device tends to be solid state. You can also find it in high-end desktop computers and high-end laptops, and the reason for this is for performance, because obviously it is a lot faster. It does have a large capacity, okay, but not as large as magnetic. It definitely has the fastest transfer rate. It is very portable. It's lightweight and compact for that purpose. It is the most expensive, however. It is very reliable and it is very durable as well. So for storage device questions, you will be expected to be able to know which one is which. So which one is the highest capacity or the most robust, etc., etc. And then using that knowledge to pick the right one for the right scenario. So when we talk about secondary storage and memory, we are normally talking about bits and bytes. So you need to know the order that these come in. This is very important because sometimes they'll ask you to convert between one unit and another. So the start is a bit, which is single 1 or 0. Nibble is 4 bits and a byte is 8 bits. Then we have a kilobyte, which is 1,000 bytes. We then have a megabyte, which is 1,000 kilobytes. We then have a gigabyte, which is 1,000 megabytes, terabyte, which is 1,000 gigabytes, and just for completeness, we have a petabyte, which is 1,000 terabytes. It is important to remember the definitions here. So a bit is a single value, a single 1 or 0. Okay, so I've circled it there. A nibble is 4 of them, as shown here, and a byte is 8. It is slightly different to when we talk about bytes and kilobytes, which is always 1,000. Bytes are made up of 8 bits. One thing you have to be really careful of with this is if the question says bits, okay, and it says to calculate things in bits, that's fine. If they then want the answer in bytes, well, that means I have to then divide the number of bits by 8. Okay, so do be mindful if the question is asking for bits or bytes, and sometimes to muddy the water a little bit, it might say kilobits or kilobytes. Okay, kilobits is 1,000 bits, kilobyte is 1,000 bytes. Well, kilobits, okay, to convert it into kilobytes, I'd have to divide that number by 8. So just for an easy calculation, if I had 8,000 kilobits, well, that would be 1,000 kilobytes. Okay, so just be mindful of the word bits and bytes, and that we can put kilo, mega, giga in front of any of them. Okay, so to convert between any of these, whatever my starting point is, okay, so if I want to convert 500 kilobytes to gigabytes, then we need to go from KB to gigabyte. So I need to go from kilobytes to megabytes, and then megabytes to gigabytes. Okay, and each time I do that, I have to divide by 1,000. Okay, so I divide 500 kilobytes by 1,000 to get to megabytes. I then divide that again by another 1,000 to get to gigabytes. Okay, and there is the answer on the screen. And then when I want to convert again, let's say I want to go from 2 terabytes to kilobytes. Well, I'm starting at terabytes, and I have to go from terabytes to gigabytes, then gigabytes to megabytes, and then finally megabytes to kilobytes. Okay, so each time I make that jump, I'm going to be timesing by 1,000. So when I go from a large value to a small one, so from, I don't know, petabytes to gigabytes, or from megabytes to bytes, each time I make one jump, I'm going to times by 1,000. Okay, and there is the calculation and answer on the screen. Okay, binary is how we will represent numbers using ones and zeros essentially. So binary is the base 2 number system. Denary, which is our normal numbers, is base 10. It's called base 2 because it has 2 values, a 1 or a 0. Denary is base 10 because we have 10 different values, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So in order to make a conversion, okay, we'll have a binary number. So let's say I had 0, 0, 0, 1, 0, 1, 1, 1. What we'll do is we have these numbers. each one doubling each time. So we have 1, well, the double of 1 is 2, double of 2 is 4, double of 4 is 8, and so on and so forth. And that's how I can work out these top things. So if you're going to do a question on this one, you'd probably write out this grid to help you. You write the binary underneath it like I've done here, and then you can work it out. Well, I've got a 1 underneath the 16, I've got a 1 underneath the 4, and a 2 and a 1. So 16 plus 4 is 20, plus 2 is 22, plus another 1 is 23. So the answer to this one is 23. So you write out the binary table. So 1, 2, 4, just double each time. Just remember it starts with 1. And notice that we are going this way. Okay. If you put the 1 on the other side on the left and then double the other way, you'll get the wrong answer. Okay. Then we write the binary underneath it, make sure everything's in the right column, and then finally we just add up the numbers on the top where we've got a 1 underneath it. Okay, that's the process. And obviously going backwards, we work out which numbers on these top will go into it. So let's say I have the number, I don't know, 17. You find which numbers have the biggest. So if I change the color here, well, in order to get to 17, I will need a 16 and I'll need a 1. So the answer is going to be 0, 0, 0, 1, 0, 0, 0, 1. Okay, so we just look at which of these numbers on the top need to add up to get to the number that's been requested. Right, character encoding is how we will store letters into binary. Okay, so the simple premise is every single letter is given a number, okay, and then because we already know how to turn numbers into binary, the process becomes really, really easy. So each letter is given a number, then each number can be turned into binary, okay, and then we have that final kind of answer. So in order to do this, we'll have a character encoding scheme, and it's known as a character set. Okay, so a character set is a complete collection of characters, letters and symbols, which are recognized by the computer. The ones that you need to be aware of are ASCII, extended ASCII, and unicode. So ASCII is used to represent English and other Western languages. We use 7 bits with a total of 128 different characters, and that is enough to store all the uppercase, lowercase, digits, and punctuation marks in the English language. Extended ASCII has an additional bit, excuse me, so we use 8 bits instead. This is very common that normal ASCII is extended ASCII is just referred to as ASCII because we tend to use 8 bits anyway. So 9 out of 10, when you're talking about ASCII, you really talk about 8 bits. Okay, and I've definitely seen some exam questions where they made the assumption that ASCII is just 8 bits. It is useful for European languages, so we have accents and we have other special characters such as the copyright symbol and things like that. The other main character set is Unicode. This one is used for representing all different types of languages, so Arabic, Chinese, Greek, Mandarin, things like that. Instead of using a single byte, we'll use 2 bytes or 16 bits, sorry, and which allows us to store 65,536 different characters, which is more than enough to store all the different languages. Notice that the key one here is it uses 16 bits. You're not expected to remember that number there because it's just a random number. So 16 bits is the key. So if you remember that ASCII uses 8 bits and Unicode uses 16 bits, that's the key to this one. Data sometimes needs to be compressed. The purpose of compression is to reduce the file size, so it reduces the amount of storage space a file might take up. Also, if I'm sending a file over a network, I might reduce its size in order to reduce the amount of bandwidth that is required. Remember, bandwidth is the amount of data I can send per second on a networking cable or networking connection, such as Wi-Fi. Therefore, if I can reduce the amount of data I'm sending in the first place, that will help speed up data transfer. It allows me to make the most efficient use of limited resources, so limited storage, limited bandwidth. And some files would be just too big to send. For example, media files, so explicitly video files would be too big to send and store without that level of compression. There are two types of compression you need to know about. Lossless. This is where no data is lost as the file is reduced. Okay, so when I compress the file, I will get a smaller version of it, but when I decompress it, I get the exact same original file. It's going to be perfectly reproduced. There's not going to be a single bit lost. So it's used for when I can't lose any data, which tends to be text files such as Word documents or PowerPoints, source code such as Python, and executable files that I can run on the computer. It's used for file types such as HTML, Python files, text documents, docx, PDFs, things like that, where there's a lot of text in it, but it does not reduce as much as lossy does. So although I can reduce this file size, although I get my exact original file back, the amount it compresses is a lot less than lossy, where some data is discarded during compression. So it actually takes part of the file and essentially throws it away, which means that when we decompress it, we can't actually get back to that original file, and we get an approximation of that file. And the reason we use it is because sometimes that data that we do end up throwing away is not essential. This tends to be used for media files, such as video, images, or audio. So when you reduce the quality of the image by throwing away some of this data, you actually can't tell when you're looking at it. So you have to kind of maybe zoom in or really listen carefully to actually notice. So it's commonly used for files such as JPEGs, MPEGs, MP3 files, and other media files like that, so video, images, or audio. Right, storing images in binary requires quite a little bit of specific information. So when I am storing an image, I am really storing a set of pixels. An image made up of pixels is little squares of color. In order to store an image, I will need an image resolution, which is essentially the width and the height of the image. So how many pixels go across the width, how many pixels going down the height. The number of bits used to store each single pixel is known as its color depth. So the color depth is essential when I'm storing a pixel. So I need to know exactly how many bits I'm using for each color. And the more bits I use, the more colors I can represent. So for example, if I'm storing a 2-bit image, I will have 4 colors. So the table here shows how many colors I can store using 2 bits. You see I've got 2 bits and got all the different permutations of it, all the different values of it, and I can assign a color to each of those, and then that's how the image will be stored. So the more bits I use for the color depth, the more colors I can use. So the quality of an image will increase the more bits I use for the color depth. However, if I increase the color depth, I'll also increase the file size. The same goes for image resolution. The more I increase the resolution, the better the quality of the image, but the higher the file size will go. Alongside the file data, we will also store metadata. So this is data about the data, and it's data we use to help us reconstruct the image after the fact. So we store key bits of information such as the image resolution, because I need to know how many pixels are in each row and how many rows I'm going to have. I need to know the color depth, because if I have a 3-bit image or 4-bit image, that makes a big difference how the data gets saved. And I also need to know the file type. So is it a JPEG? Is it a GIF file? What's the type of file? It may also store additional data such as the author, the location, or other bits of information such as that. In order to calculate the file size, which tends to be maybe the tail end of one of these questions, we need to know 2 bits of information. We need to know its resolution, which is the width and height, and we also need to know its color depth. So when we do it, the calculation we use is width times height times color depth, okay? And this is always going to be an estimate, okay? Because we also add on the the file, the metadata, and also remember I might use compression as well. So in order to do it, we take the width and we times it by the height. Okay, so I've got a width of 200 in this example, a height of 10, so it's going to be 200 times 10. And then the color depth in this example is 8, so I times that by 8 as well. So I've got a width of 800 pixels, a height of 10 pixels, and a color depth of 8 bits. So multiplying those two together gives me 16,000 bits. And then in order to calculate how many bytes it is, okay, I need to divide that number by 8. If I ask for the answer in kilobytes, well, that would be 2, because I simply just divide that by 1,000, and then I can write out 2 kilobytes as my final answer. Sound is an analog wave. That means that they are continuous. So every time I zoom in, I will still have more detail to look at. Analog waves can't be stored digitally. So in order to store it, I need to sample it. Okay, and a sample is when I record the amplitude of the sounds at a certain point. So how often I sample is known as the sample rate. So that's a frequency because it's the number of times I do something per second. So the image here on below shows a wave that has been sampled, and you can see I've drawn a little bar chart almost to represent where that amplitude has been recorded. So the biggest issue with this is that obviously I'm not going to get a perfect reconstruction of that sound wave, but it's going to be like that best fit. The higher the sample rate, the more accurately I can represent that sound wave, the more closely it will look like the sound wave, and therefore the higher the quality. But obviously, as I increase the sample rate, because I've got more data to save, that will also increase the file size. So increasing the sample rate will also increase the file size. Sound files tend to be measured in something known as bit rate, and this is the number of bits that need to store an audio file per second. Okay, and it's calculated by taking the sample rate and also multiplying it by the sample resolution, which we're going to look at next. So the sample resolution is the number of bits I use to record the amplitude. Okay, so the more bits I use to record that amplitude, the more kind of fine detail I can place into it. It's going to be a denary value, so very similar to color depth, where the more bits I use, the more colors I can represent. With the sample resolution, the more bits I use, the more kind of individual or fine detail I can store for each amplitude. Okay, so increasing sample resolution will increase the quality of the sound, but also on the flip side will increase the file size. So to calculate the bit rates, we need to multiply the sample resolution by the sample rate. Okay, so if the sample resolution was 6 and the sample rate was 1,000 hertz, that's going to be 6 times 1,000, which is 6,000 bits per second. Okay, and it's measured in bits per second. That's because the sample resolution is measured in bits. Sample rate is the number of times I do something per second as frequency, so it's bits per second. Calculating the file size is going to take that bit rate and multiply by the sample length. Okay, so this bit rate is how much data I need to record 1 second of audio. So if I've got an audio which is 20 seconds long, I simply take the bit rate and I multiply it by 20. Okay, and that will give me the number of bits it required to save the file. I then, like before, might divide it by 8, which will give me my final answer in bytes. You may also be asked to turn that into kilobytes, which is just simply going to be dividing by 1,000. Now let's look at the different hardware required to set up a LAN. So network interface cards are required for any device that's connecting to a network. Okay, this might be wired or wireless. These tend to be built into motherboards and built into devices nowadays, so you don't tend to have them as separate components. However, you still require them to connect to the network. Inside a LAN, we might have multiple computers which we want to connect together using wires. Okay, it's very important that a switch is used within a LAN only and is used to connect devices wired. Okay, so a device would plug into these ports on the front of the switch, and then what this switch will do is it will route packets to the correct destination. Now, the biggest misconception people have is that a switch will route packets and a router routes packets. They both do a similar job but in different purposes. Okay, so MAC addresses are used inside a switch to route the packets. Okay, so inside a local area network we will have a switch, and then the switch will use MAC addresses in order to send things to the correct destination. Also inside a local area network, we might have wireless access points. So wireless access points will allow you to connect wirelessly to a device. So we'll use wireless signals to connect to a device, so such as an iPad or iPhone. We'll send wireless signals to the wireless access point in order to connect to the network. The wireless access point would then might be connected to a switch using a cable. In a large organization, such as a school, there'll probably be many of these wireless access points because they have a limited range. They do suffer from interference, and obviously the more people connecting to a wireless access point, the less bandwidth each individual person will get. So one of the other parts of networking is known as networking protocols. So in order to send a message across a network, we need to ensure that both devices know exactly what that data looks like. And this is known as a protocol, which defines a set of rules of how devices are going to communicate. So devices communicating with a network must use the same protocols, otherwise they won't understand each other. These protocols are defined as a standard. Okay, so different groups of manufacturers and software engineers basically all got together and decided, okay, this is how HTTP will work. Okay, this is how TCP will work. This is all then written down in a standard, and then anybody who's writing software to interact with TCP or to interact with HTTP or whatever protocol we're talking about must ensure they meet that standard, meet those rules. Okay, so a protocol is a set of rules that governs communication, and a standard is what's been agreed between a group of developers and manufacturers about a certain area. For example, like ASCII and Unicode. So email protocols sometimes gets a bit of confusion. So there are two sets of protocols we use. One for sending email, which is SMTP or Simple Mail Transfer Protocol. This is used to send emails because it works differently to receiving them. So when I send an email, I have to send it to my email server first. Okay, so let's say I had a Hotmail server address, it will go to Hotmail. Then let's say I was trying to send an email to Gmail, so the Hotmail server will then send an email to the Gmail one. Okay, so it requires two email servers potentially in order to send the email. Receiving email has two different protocols. We have POP3 and IMAP. And depending on how I'm going to be interacting will depend on which one I use. If I'm only ever going to use one email client, so either just my phone or my desktop PC or whatever it happens to be, if I only access my email on one device, then I can use POP. POP will delete the email from the server as soon as it's read. IMAP, on the other hand, is useful for multiple clients. So if I read my email on my desktop PC, my laptop, and my iPad, and my phone, then I've got 4 different clients all reading the exact same email. So that email is saved on the server and is synchronized between all the devices. So if I delete the email on one device, it deletes it from all of them. And if I leave it and don't delete it, it can be seen by all devices as well. We then have the more website ones, so you have HTTP and HTTPS, so Hypertext Transfer Protocol, and this is used for transporting all the files that are required in order to load up a web page. So that's going to be including the the HTML file. It's going to be all the images, the videos, and anything else that's required in order to display that web page. FTP is not commonly used anymore, but it's used for transferring specifically files on a special file server. Okay, it isn't common anymore. It used to be very common, but not used very much. Sometimes used for web hosting. So if I had a website hosted on a server somewhere in the world, I might upload my files using FTP and download them if I need to from FTP. The last ones you need to be aware of are the two named ones in the TCP/IP protocol stack. Basically, protocols are layered together in 4 different layers. We have application, transport, internet, and hardware. So the 2 main protocols which are used by most of the networking communication is TCP and IP. So TCP stands for Transmission Control Protocol, and its job is explain how packets are split up. So remember, if I've got a really large file, such as a video, which I want to send across the network, rather than sending that one big file in one go, it chops it up into little parts and then puts them into a packet. That packet is then ordered, so we know which order it should come in, and it has error detection just in case it gets corrupted for whatever reason or it doesn't arrive, for example, and that way we can make sure that we can reconstruct the final file correctly. Then we have the Internet Protocol, which is used by all communication, and this has the job of routing the packets across a wide area network. Now remember that a router is used to connect different LANs on a wide area network, and they will use the IP address. So the Internet Protocol is designed for routing packets across the internet. Networking performance. There's 2 key areas here. The first one is bandwidth. This is not necessarily a measure of speed. It's a measure of how long it will take a file to get there, which does sound like the same thing, but it's ever so subtly different. We measure bandwidth in bit rates. So how many bits per second can I send? So it's the amount of data that I can send per second, not how fast that data travels. Okay. We tend to use either megabits per second, gigabits per second, and sometimes kilobits per second. The other thing to bear in mind in this one, it's measured in kilobits. Okay, the bit rate, not the byte rate. So it's not the number of bytes per second, it's the number of bits per second. That is an important distinction because when we are doing calculations, we can't say, oh, it's a number of bytes being sent per second, because that would be technically incorrect. So let's say we had a low bandwidth connection and I had a number of packets. So let's say a big movie that I want to send. Those have been split into packets already, and the amount of data I can send at once will depend on the bandwidth. So if I've got low bandwidth, I can only send part of that data at once. If I have a high bandwidth, then I can send more of the data at once. Okay, it allows me to send that data quicker. The second networking performance thing you need to be aware of is latency. Now, latency is the amount of time it takes for a message to go from one PC to another and back again. Okay, sometimes known as the ping rate or ping. It's very common to see the ping rate in online gaming because obviously the ping rate, the latency, is super important. If there's a high latency, this is bad because it takes longer for the message to come back. So if I'm playing an online game, then I will start to notice lag in my game. A low latency is better. So the key to remember about networking performance is bandwidth A high bandwidth is good, low bandwidth is bad. High latency is bad, low latency is good. Latency can be impacted by lots of different things. For example, weather conditions, the amount of traffic on the connection we're using. If the cable is longer, that does impact it, and how much the server is under load. So how many devices are connected to it, and how many devices are using it at once, and what they're doing as well. Right, preventing networking threats. There are a number of ways to prevent networking threats. Most of them are fairly straightforward. Firewalls is probably the new knowledge that you would need to know. And what firewall will do is either a software or hardware solution that will look inside every single packet that travels through it. It will make sure that that packet meets a set of rules that's already been defined. If the packet does not meet those rules, then that packet is discarded. It will look inside the packets, which means it can spot potential threats, for example, like denial of service or other threats along those lines. So it allows us to have more of a deeper look at the packets themselves and be able to discard any invalid ones. Other protection methods you're probably very familiar with. So anti-malware software, so for example antivirus software or other types of malware. This is software you'd have installed to prevent these threats from being installed. Having a good sensible password obviously is key, and not having that same password on multiple devices. Different user access levels, so different groups within an organization might have different access rights. So for example, in a school we'd have student access level, so they can access some parts of the system. You have a teacher level, which can access more parts of the system, and then you might have a senior leader and maybe the head who can access everything. When I'm sending data across a network, if that data is sensitive, for example, maybe my credit card number, then I may wish to encrypt it to ensure that if it is intercepted on the network, so if using a man-in-the-middle attack, then that data is still secure. Okay, so compression is used very commonly over the internet, especially when sending private data. And if you look at websites, you'll be able to see the little lock icon, which lets you know we're using HTTPS or HTTP secured. Let's look at the legal aspects now. So the Computer Misuse Act is the act which prevents unauthorized access and use of a computer. So it is a criminal offence to have unauthorised access to computer material, so i.e. access to something on the computer which you're not allowed to. Unauthorised access to computer with the intent to commit a crime. So for example, trying to access a file and blackmailing someone to get it back. And unauthorised modification to computer material, for example, logging in and trying to change how much you earn per month. So these are three aspects of Computer Misuse Act. It doesn't specifically state hacking, so please don't write hacking down as what it is. However, in order to gain unauthorized access, I might hack. It also might be that I know figure out someone's password by tricking them into it, so using phishing attacks, for example, or it might be that someone's left their computer unattended, walked off, and then I have access to it. Now, I'm not allowed to do that. I'm not allowed to use someone's computer if they're not there. However, I haven't done any hacking to get there, if that makes sense. So computer misuse governs all unauthorized access, not just hacking. The second law is the Data Protection Act. You need to be aware of the new Data Protection Act, but in all honesty, it's for GCSE, it is pretty much the same as what you had to know. So any data that is collected by schools and companies need to be protected by securing that data. It can't be collected if it's not required. So companies are not allowed to record data that they're not allowed to or have a reason to use. They need to make sure that they have a data protection officer, so someone who's responsible for looking after that data and ensure it's used correctly. And also they need to make sure that the data is not excessive, and is only stored for as long as they need to. One other key things about Data Protection Act is that you need to have permission to record that data unless that data is required in the execution of an essential service. For example, like in a school, you can't request that we don't record your I don't know, test results, for example, or your green stamp totals, because we need it in order to be an effective school. Okay, so companies can only collect data without permission if it's essential to giving a public service. So, for example, like recording medical data in a doctor's surgery. It is very common that your legal and ethical style questions tend to be those long answer questions, which have to be answered a bit like a white paragraph. So when you read these questions, you need to decide whether, what topic is this question related to? So what knowledge do you need to talk about? What facts will help you answer that question? Then how do I link that fact back to the question? Do I need all the facts, or can I be selective about which facts I'm going to include? So ultimately, is the fact relevant? And why does my response answer the question? Making sure that have I answered the question, does what I've written kind of meet all the points of that question? So this is really simplified, but the questions are broken into low, mid and high, and ultimately for high bands you need to look at all aspects of the question. What you write needs to be accurate. All the points are linked back to whatever the topic is. In this example, it would be to do with a medical AI, but essentially linking every point that you make back to whatever the scenario was. Making sure that all your examples are relevant and not superfluous. Discuss the impact in the area, so how, not only just stating one thing, actually linking that back and say, well, what impact would that have? And making sure that obviously there's a structure to your answer, using paragraphs, you're thinking about it, you're not just bouncing around all the place. And then obviously mid-band and low-band, you'll not necessarily have that. So for example, in mid-band, you might have the odd mistake, not every point is linked back. Most of the examples are relevant, maybe there's the odd weird one in there that's not relevant, etc, etc. So the way you will answer these questions is you'll work out, okay, well, what topics are these looking at? So in this scenario, it says legal issues, and it's talking about medical AI. So you might decide actually this is linked to the Computer Misuse Act and maybe the Data Protection Act. And then what can you draw out of that? Okay, what's the implication of that? So if we talk about the Computer Misuse Act and I'm storing lots of sensitive information about people's medical history, well, hackers might gain access to that data. That would be the facts. If I'm about to fire a load of people, well, that means that fewer people are going to be there to look at the data. So Data Protection Act also covers data being looked at by other people inside the company, as well as what data is being stored. So once we have got those facts and we know what topic it is, we've picked what facts we're going to talk about, we might expand on them and link it back. So for example, if I was going to talk about hackers and the Computer Misuse Act, I might say that medical data might be very sensitive and might be a target for those hackers. So all I've done is I've taken the point and I've expanded it and linked it back to the question. Okay, so I take my key points, figure out what I want to say about it, and then expand it by linking it back to the question. Okay, that's how you get into that high band. What topic? What fact do you want to say about that topic, and how can I link it to answer the question? Okay, that's the secret to long answer questions.